This presentation is on hypothesis testing for proportions. This is in terms of the binomial experiment. Either the event happens or it does not happen. If you try 3 times with equal probability, then the expected number is 1.5, and therefore normal approximation to the binomial does not apply. However, as the sample size increases, and we come up with a binomial experiment where the expected count in each category is at least 5, then we are justified in using normal approximation to the binomial. That is, if the assumptions are satisfied, we have at least 5 in one category and at least 5 in the other category, then we can set the mean equal to NP and the standard deviation equal to the square root of NP1 minus P, and this new variable is approximately normal. The test statistic is the number of successes minus the expected number of successes over the deviation, or we can write this in terms of proportions. The test statistic is the relative frequency minus the population parameter p over the square root of p times 1 minus p divided by n. Then, treating this as normal, we can do the calculations of standardizing the data and then computing the likelihood to make a decision. Consider the following example. In 30 trials, given 20 successes, test the hypothesis that this is 50%. That is, the null hypothesis is that this proportion is 50%. Alternatively, we believe that the proportion is greater than 50%. Using the standard score in terms of relative frequency, we can compute the test statistic and determine the p-value. Then, comparing the test statistic to the critical statistic, we can make our decision, or we can compare the p-value to the alpha value and we will reject the null hypothesis. At the 5% level of significance, there is sufficient evidence to reject the null hypothesis. Consider the following example. In a sample of 45, 27 agree with a given amendment. The relative frequency is 60%. Test the hypothesis that this is 2/3 majority. That is, the null hypothesis is that the proportion is at least 2/3. Alternatively, we believe it is less than 2/3 as we have only observed 60%. Computing the test statistic, we get negative 0.95. With a p-value of 17%, this is insignificant. This is further illustrated by the critical value. At the 5% level of significance, there is insufficient evidence to reject the null hypothesis. In a sample of 45, 60% is not significantly different than 2/3 majority. In this example, a candidate claims that he has 60% of the vote. You take a survey and compute the numbers to test this hypothesis. First, we will need to determine the counts of how many people said no and how many people said yes. This is done by using a count-if statement. Count if in column A, it is equal to what is in column C2. Then use autofill. Then we can sum these two numbers to find the total sample size. The relative frequency is the number of yeses divided by the sample size. The null hypothesis was that p is equal to 60%. Alternatively, we will test that it's less than 60%. Our test statistic is the relative frequency minus the hypothesized parameter value divided by the standard error, which is the square root of p times 1 minus p over n. Therefore, we can measure the likelihood, or the p-value. The p-value is based upon the standard normal probability distribution, so the standard normal distribution of the given value. Therefore, at the 1, 5, and 10% level of significance, we will fail to reject the null hypothesis. 52.27% is not significantly less than 60%.